Hi everyone, welcome back to my channel. Today we're diving into something really cool, building a Siren detector using neural networks and sound recognition. This project was inspired by the TinyML Fundamentals course and Nicholas Renaud's bird sound detection video. I will drop links in the description if you want to check this out. So, what are we making? A program that will hear and identify emergency sirens, like ambulances and fire trucks ones. Don't worry if you are new to machine learning, I'm going to learn this too. This is not about perfect ML practices, it's about having fun while building something useful and learning something new. Here is our goal in the nutshell. We will capture a sound through the microphone. Here we have a sound source, here we have a microphone. We'll capture sound through the microphone, process it with some clever software running on the PC in this case, and show detection results on a dashboard. We will start with PC version today, and maybe I will optimize it for microcontrollers in one of the future videos. First things first, let's make it simply work. To build our siren detector, we need four main components. Think of them as team members of Siren hunting squad. First of all is the preprocessor. It's a translator from the raw audio that will come from the microphone to something that our model, our AI can understand. Next will be the classifier. It's like a detective that examines the processed sound and looks if there are some siren patterns or not. Then we have interpreter, interpretation model. It's a decision maker that converts AI's complex answers into a simple response, yes or no. And then we have a dashboard. It's like a messenger. It's something that will show us the results in the form that we can understand. Actually, the final result of all this chain will quite simple and easy to understand answer. Was there a siren or no? There was no siren in this audio. Let's discuss technologies that we will use to implement all this chain. We will use Python and Python libraries for neural networks. Why Python? Because it's easy to write on, it's easy to learn, and it has lots of tons of ML libraries ready to use. And this makes the prototyping in Python super fast. We will use TensorFlow for the classifier for our, let's say, brain of our detector. It's a popular machine learning framework, and many real-life AI applications use exactly TensorFlow framework. Is it most efficient approach? No, because the Python is not really fast actually. Uh, Probably C or even Golang interpretation will be faster at the runtime. But our goal here is to learn how this should work. Our goal is to make it work at all, not to optimize and not to make it portable in this video in this run. So we will use Python and TensorFlow to make it work. Now let's discuss the elements of our chain one by one, and let's start with first one with the preprocessing. What we want to do here? First, we will grab our sound from microphone or from the audio. We need to read data from the file, or we need to read the data from the microphone. Then we need to, let's say, normalize it. We need to do some housekeeping with transferring the data from stereo format, transforming the data from the stereo format to mono format. We need to adjust the frequency maybe, and then we will do real magic that will convert this raw audio to something that our neural network can understand. We will convert audio to something like this. It's called spectrogram. Spectrogram is what is it? Let's imagine that we chop our file into small pieces and we figure it out which frequencies are present in each piece. It's like approximating decomposing audio into individual notes, individual frequencies. So we will have 2D, two-dimensional image at the end of this process. Here we have frequency, and it's about breaking the file, breaking the audio on a pre-configured number of frequencies. It's not a continuous value here. And here we have time. And here you can see actual sound of this. Oh, sorry. This will be next slide. Actual sound of the siren. So frequency goes up and then it goes down. Yes, we will lose some information in this converting process, but for detection purpose, visual representation of sound works brilliantly. It will be easier to process it, and we can always just save it as a picture and see what data we have there. It will significantly easier our life when we will debug something. Actually, right now we converted the sound to something that our neural networks can understand, can, let's say, see. Let's talk about the next element in our processing chain. It's the classifier. Do you ever wondered how our brain instantly recognizes a siren while we are driving? Well, we will build something similar, but with using math. Since we cleverly transformed audio into images, into spectrograms at the previous step, we need neural networks that can easily recognize patterns in images. And here we have convolutional neural network. The superpower of these neural networks is the following. While regular networks are looking for individual pixels like separate dots without connections between them, convolution network is trying to look at the whole picture. It's just like you don't see individual dots when you're looking at the photo. Here we have special slide filters that slides across the image and they looking for patterns. Like you might scan where's well the picture that for that red and white striped shirt. Here is what happens inside the convolution neural networks. First, it hunts for some simple patterns like lines and edges. Here we have feature maps for really simple patterns. Then it tries to combine it into more meaningful shapes, or maybe not meaningful in our sense, but in something that often presents in samples that we want to look at. And here we have next layer of convolutions that will look for combinations of patterns we found at the previous steps, and this will repeat sometimes. And after that, we will have a fully connected classifier that will tell us that okay, here and here and here we see something. This means that we have image of that class. So first layer is looking for really simple things. Next, it tries to combine to more complex patterns, let's say. And with increasing depth of the network, we have more and more intelligent pattern searcher. And finally, it will be able to make a prediction, make a decision that, yeah, it's a siren, or no, it's a just traffic noise or silence or something else. It's not a siren. And coolest part of this, when this convolution network is fully trained, it will recognize these siren patterns even in noisy situations. It's like having a friend who can hear a fire trucks 3 blocks away while you still wondering what is that sound. I will not specially cover the interpreter part because for this particular project it will be really simple. We will just look at the output of the network, of the convolution network, and if prediction for the siren will be more than some specific threshold, for example 95%, we will just think that okay, siren is detected. For us, all other situations, we will think that no, it's a noise, it's a traffic, something like that. So here we have really simple logic, and I will not especially cover it. Maybe we will return to this when we will examine the code. But let's cover another thing. Even when our classifier is fully programmed, we need to train it first. We need to train it to make it an expert, to learn it how to detect the sirens. Uh, Training or and using in ML language, this using is inference and training is called also training. It's a completely different things. Inference it's a real world application. It happens all the time while this project will work. And training is something that happens maybe one time, maybe it happens not so frequently while we getting some new fresh data and we need to adjust, fine-tune our network on new data. So, but we have to train system first before we can use it. Training is really fascinating process. We will bombard our network with thousands of sound clips, with siren, with traffic, with maybe silence or some noise, and again silence. The network will guess actually at the very beginning because it's initialized randomly. But with our training script and with the help of TensorFlow library, we will learn it, we will adjust its internal state, so it will slowly but surely learn how to recognize our pattern, our sirens. So here is what the training script will do. First of all, it will gather our dataset. We have to download it, we have to prepare it. More is better. More is better in that case. It will transform our dataset. It will preprocess like we see before. It will convert it to the spectrograms. Next, it will create convolutional neural networks with architecture that we will hardcode them there. It will fit our examples and perform the training itself for prolonged, maybe prolonged time for lots of repeats. Then it will try to feed some data that was not used in training. It will quiz it with sounds that it never heard before, and then it will save the model. After all the operations, it will save the model, so we will able to use it later. Well, when this process is finished, we will have just a compile small model file. It's a distilled knowledge of thousands of silent examples packed in just one file. Best part is we can use it anytime later without this long, lengthy training process. It's like graduating from high school. Learn once, apply forever. With that said, let's move to dataset obtaining and preparation phase. With a high-level architecture of our solution discussed, we can move to the implementation phase. And obviously, we should start with the dataset. We need at least something to start with, because in ML projects, dataset is the key for project success. I propose to use this dataset, emergency vehicle sounds, siren sounds from the Kaggle. Yeah, it's maybe not perfect, it's quite small, but we can start. At least we can start with it. And I hope at the future project phases I will implement fine-tuning on the real sounds that our detector can hear. But for now, for start, this should be good enough. So please register yourself on the Kaggle site. Go to you can find a link to this dataset in the description and in the README file for the code. Go to this dataset link, press download, and download this dataset as a zip file. This will be good enough for start. Once you have downloaded the dataset, you will get this archive.zip file. And that's good enough for start. Let's unpack it and a bit rearrange it. I will show you what I mean a bit later. Let's first unzip it. You will find all the comments in the README file, so don't try to remember this. First we will unzip it, and what do I mean by rearranging? You can see categories of the objects, of the sounds. Here you can see three categories: ambulance, fire truck, and traffic. But we need only two classes. We need a class for siren and not siren. So we have to move these two classes in the one folder. And I think we should rename traffic to like something like other, because we don't interested in traffic. We're interested in detecting siren versus no siren. So let's rearrange it a bit. Let's create directories for siren sounds and other sounds. And let's just move all the, as you can see, we have audio files for each sound sample and we have spectrograms for each sound sample. We only interested in audio files. So let's move. Let's move siren and non-siren sounds in appropriate folders. One moment. And we have the following. We have siren sounds in siren folder, and we have some other sounds in other folder. So we have examples for positive class and for negative class. Yes, the dataset is unbalanced. We have two times more samples in Siren folder, but for now let it be like this. Yes, I know that this is not perfect scenario, but we can at least start with it. Let's clean up a bit. Perfect. And now we can move forward. We have the data properly arranged. Congratulations, we can move to the code. Let's briefly take a look at the code. We will start from train function, train file, just because it's simpler and we have to train our network first before we will able to use it. So what do we have here? We have a couple of helper functions. They will load the audio file, convert it, and convert it to spectrogram. So with two functions like this, we can transform raw audio files to graphical representations, to spectrogram, which we can use later for our convolution network. So what do we have here in the main code? First of all, we will fix the random seed. We need to do this because network is initialized with random values, and normally from one run to another you will get slightly different results. And if you change something, if you experiment with network architecture, if you experiment with dataset, something like this, you probably want to be sure that changes that you're observing is changes because of what you altered in the files, not because just it's a different random. So because of that, for testing phase, for developing phase, we will fix the seed. Then we will load the files, and because we want only detect if there was a siren or not, we will only use two classes, positive and negative. And for positive, we will load the files and just put one as a label. So we add this is a detection, so we have one here. And for negative class, we have 0 as a label because there is no siren in that files. So after that, we have raw data that consists of our spectrograms labeled with ones or zeros for class with sirens and class with all other noises, all other sounds. Then we will preprocess that data with this function, and we will do some optimizations. We will cache this dataset to just make training a bit faster. Then we need to have a test set, so we will use part of our dataset as a train and part of our dataset as a test. Here we have some debug output to see amount of data that we have, to see tensor shapes just for debugging. Now we creating our network. As you can see here, we have lots of layers, like it was shown before on the presentation. First of all, we have a square-shaped label, not square, rectangular-shaped layer, and with height and width equal to our spectrograms. Now we will just resize it a bit. We can resize it to different size. We can resize it a bit more, but in that case we will lose some data and we will lose some accuracy. So let it be in that size for now. Then we have the convolution layers. At first we want them to have to be bigger, and we have more convolutions at the beginning just because we want sorry, not we want them to be bigger because here is window size and it is exactly the same. We just want them more of them just to catch more details. Then we will do some pooling, again convolutions, but on the smaller, let's say, canvas. And after that, we will just flatten it from 2 dimension to 1 dimension, and we will have just one fully connected dense layer, 128 neurons, which will analyze our results from our convolutions, and it will decide if there was a siren or not. At the end, we have just one neuron, one output with sigmoid actuation, so this one will decide if there was a siren or not. As I told before, I only learning, and this is actually my first hands-on experience with TensorFlow. So I sure that you can say, okay, dude, we want to catch sirens. It should be more than three on three convolution window. Yeah, I agree. This is really far from optimal network architecture, but it works. And I will try to enhance it. I will try to make it more reliable and more optimal in next videos. For now, I just want it to work, maybe not perfectly, but to make it just work. So we compile this model. To make it able to train, we print the summary of the model, what do we have there, and with this function, we actually train it. So here we have training data. We have 10 train epochs, which is quite small, but because we have quite small data set, it's more than enough for this phase of the, let's say, of the project, for this phase of the test. So 10 epochs should be good. I tried to make more epochs, several thousands of epochs, but it don't makes difference at the it's not makes difference on how the network behaves after that, just because we have too small data set, I believe. So after this function will finish, we will print results. We will print accuracy of our network, and we will just try to predict on test samples, just to make sure that network works at all. And after that, we will save this model as a keras file, so we will able to use it later. Just to be sure, we will reconstruct the model. We will just load model from that file and try to predict the same samples like before, and we able to compare if what we have from loaded model is more or less adequate or not, just to be sure that load and save functionality works as we want. Okay, now let's try to start this model training file and see what happens. Okay, let's run the training of the model. It will take some time, so I will speed up video a bit to not make you wait for too long. Just let's take a look at the model statistics, and as we can see, we have crazy model size for this small task here. Yeah, it's because we have lots of parameters, lots of parameters in these layers. So combination of parameters will have quite big size. But as I said before, for now we don't want to make it ideal. We don't want to make it small as possible. We just want to make it run. So let's wait a bit and see what happens. Will it able to distinguish sirens or not sirens on the test set? Let's see. So finally the training is over. And here we can have can see the loss graph over the epochs, and precision graphs over the epochs. And as you can see, it's quite fast. It reaches almost one or exactly the one. This means only that we have too small data set. But again, it's something to start with. So let's move on with this. Here we have a recall dataset, and again, quite fast. It's reached one at the epoch number 2. So our network is trained. It's saved. Here is a prediction result for test set for the original model, and here is a prediction result for the test set for the saved model. Yes, and as you can see, they are exactly the same. So our saved model works, and we can use it for our inference part. Let's move to the inference code. This is the code of the detector part, so it's an inference part. It's a bit more complicated than training part, but I will explain you all of this. Let's take a look. We also have some helpers here. First of all, we have helpers for getting the data from the microphone. And here is the first thing to consider, because when we have training part, we already have files with sound already recorded. All chunk of the sound is located in file, so we can just read it at once and process it somehow. But here we rather have a continuous continuous flow of the data. So we cannot just read some part and analyze it and that's it. No, the data is arriving consistently, and the thing is, while we analyzing something, the data keeps flowing. The world is not stopping at the moment when we process the data. So we somehow need to do our processing more or less continuous, and we need to do our sound collection process continuous, not more or less, but fully continuous. And then we should perform detections as fast as we can on that data that we collected. So how we can do this? We have array for 3 seconds. This is elements in array, and because we have 16,000 16,000 sampling per second, so we have maybe oh no, I'm not wrong, because we also have formatting, so it's not 1 byte per sample, it's 2 bytes per sample. So yeah, here we have array for 3 seconds of data. And what we will do here is we will get one chunk, 0.1 second. Here we have this one chunk. Chunk size is 1/10 of the second. So we read the chunk, we shift our data, we shift our existing data, let's say, down for that 0.1 second, and we took fresh data and we apply a part of the previous data there. So 10 times per second, this array is refreshed with latest data. And we have 3 seconds of continuous audio in a buffer. We just have this buffer rolling. We have like a rolling window, but we have 3 seconds of latest audio there. And when we will do inference on that, we will see if there was siren or not, even if we're not doing the inference at the exact same moment that the siren is arrived. So we have a rolling window for this. Here we also have helper functions for performing the inference itself. So we will preprocess the data. Here you can see these preprocessing functions. It's actually the same like in training part. So we will convert audio to spectrogram, and then we will just do model prediction. And with mutex, we will write this to the result buffer. Why with mutex? Because we have to run this all in multi-threads because when we do the inference, this thread is blocked, and we want to continue recording while we analyzing what we already got. So we have mutexes there to make this multi-thread system work. And here we also have some helper functions to drop MQTT message when we have some detection or we have the situation when there was some detection and it's disappeared. In that case, we will drop a 0. So let's take a look at the main thread. We will start several. We will start actually 2 threads for processing the data and for collecting the data. And we will just in endless loop perform processing, perform collecting, and in main loop we will just quickly take a look at what do we have from the processor part, and if we have if you have a result more than confidence threshold, it's 0.91, so it's 91%. If we have confidence more than this threshold, we will set a detection flag, so we will think that, okay, there was a detection, and we will drop a MQTT message. Also, here we have graphs refreshing, so we will visually see what is the confidence score right now and what was the spectrogram right now. It's for mostly for debug purposes because we don't really need this for detector to work, but we want to see what happens. And here actually it's a finish part that will trigger when we will stop this detector. So actually it's quite easy. We have to collect the data. We have somehow make sure that collecting process is continuous because we don't know at which moment processing will start, and we we have to have more than 1 second of the data to ensure that we have some increased chances of getting the siren if detecting the siren if there actually was something. We perform detection, so we run our model against the collected data and we just analyzed the results our model is provided, and we act basing on these results. So this is our decider part. It's a part that look at the model output and make a decision if there was something or not. It's quite simple, as you can see. So yeah, it's actually it is how it should work, at least from the code. Let's take a look how it actually work on the real system. Let's take a look at the actual setup with code that I showed you some minutes ago, actually working. So what do we have here? It's Raspberry Pi 5 with Argon case, and we have some additional cooling installed because it's not overheating, but it's about to overheat. It's about to throttle. Here you have see output of Python code running, and as you can see, these numbers, it's time per one inference. So for one loop, for one analysis, it takes 0.6 of the second. And because we have this rolling window of 3 seconds, we have several chances to get a siren sound if there was something. Yeah, here we have a microphone, omnidirectional one. It's connected with the USB cable to the Raspberry Pi. And here you can see spectrogram. Here you can see the confidence score. If we will add some noise, I hope you can see that this noise like fading on that spectrogram from top to bottom. You can see some sounds here. Maybe you can hear some background noise here. And as you can see, confidence score sometimes goes up, but in general it's quite low. Now let's artificially turn on the fake siren sound. And as you can see, confidence score is raised to 1. So, as you can see, generally it works, it reacts on the background noises, but it not gives us 1.0 confidence on the background noise or on my voice, but it works on the sirens. It seems good, yeah? But, well, it works. So, for the educational purposes, it looks good, but actually it was quite high, but it was not exactly the one, but yeah. Actually, it has some drawbacks, because this dataset was collected on the streets. It can only adequate or more or less adequate react to the street sounds. And because we have this microphone inside of the building, we may have some sounds not typical for the road traffic. For example, we can have something like this. It's a portable vacuum cleaner. Oh no, don't turn off. Let's see what happens if I will turn this thing on. And we got clear and strong false positive. So, yeah, there are obviously things to improve here. First of all, it works, but it requires lots of computational resources on the Raspberry Pi 5, which is quite powerful actually. It requires 0.6 second per one inference. It has some false positives, and it has a really small dataset. So in future, one thing to increase is to collect the sounds that this thing counts as positive samples. Maybe randomly collect the sounds that this thing counts as a negative samples, and somehow enrich the original dataset to make it more reliable against home appliances sounds, and to make it better. But as I said, for now, for educational purposes, it seems quite good, as I think. Where you can use this, for example, if your cat flushes the toilet, you can do something like this, but use another dataset, and you will be able to detect the sounds when your cat do some things that you don't want him or he to do. So this is how you can create sound detector with Python and TensorFlow. Please take a look at the comments, write your thoughts there. Please take a look at the description. There you can find links for another interesting video about this that I was inspired with, and to the great educational course that I can recommend you to watch. Thank you for watching. Please let me know what you think, and see you next time. Thank you. Bye.